Today, we're going to delve into the important concept of disconnecting the directly connected impervious area, often referred to as DCIA. This method is a highly popular and effective strategy for significantly reducing annual runoff volumes. By implementing this technique, we can realize many of the crucial benefits that green infrastructure provides. Properly understanding and applying the disconnection of DCIA is vital for successful stormwater management. Many of you are interested in the concept of the directly connected impervious area, or DCIA. We'll define what DCIA means and illustrate the impact of changes through an example project. To begin, we can calculate S prime, which represents the potential maximum retention in inches, using the formula 1000 divided by the curve number, minus 10. For instance, if our curve number is 78, S prime calculates to 2.8 inches. However, if the curve number is lower, say 50, the potential retention increases significantly to 10 inches. A critical point to remember when dealing with composite curve numbers is that the calculation must be based on the volume of discharge, not a simple arithmetic average or an area-weighted average. For example, simply taking a simple average curve number of 86.5 would lead to inaccurate results because it doesn't account for the volume of flow. Here we'll define a few important terms, drawing directly from the Applicant's Handbook, Volume 1, from June 2024. First, directly connected impervious area, or DCIA, refers to any area covered by a building, impermeable pavement, or other impervious surfaces. The key here is that these surfaces drain directly into a conveyance system without first flowing across enough permeable, vegetated land to allow for runoff infiltration. When we can disconnect these impervious areas, it's beneficial because it significantly reduces the annual volume of runoff as well as the pollutant loading. So, how do we determine if an impervious area is considered disconnected? By definition, flow is disconnected if it travels as non-concentrated overland flow for a certain distance over pervious areas. Specifically, this means flowing over at least 10 feet of undisturbed pervious areas if the soil is a hydrologic soil group A or B, typically sandy soils. For other soil types, a longer distance of at least 20 feet of undisturbed pervious area is required. Alternatively, an applicant can demonstrate that a narrower width of flow would still provide sufficient infiltration to disconnect the impervious area by percolating the desired runoff volume from a specific storm event, a 3-year 1-hour storm. These types of storm events are usually associated with rainfall totals greater than 2 inches. Our primary goal in managing stormwater is often to capture and infiltrate runoff. We've found that capturing the annual rain volume up to about 2.25 to 2.4 inches, which corresponds to typical 3-year 1-hour storm events in many regions, results in at least 95% annual capture effectiveness, provided the soils have the capacity to store that water. Hydrogeologic soil group A soils, or A soils, are particularly effective because they have the potential to store more water than what falls during a significant rain event, such as a 3-year 1-hour storm that might produce 2.4 inches of rainfall. Now, let's consider a practical application. What is the width of an impervious area whose overland flow can be fully infiltrated by a 10-foot section of HSG-A soil with a curve number of 50? Using the calculation shown, we find the answer is approximately 32 feet. This calculation essentially takes the difference between the soil's storage potential and the rainfall from the event, divides it by the rainfall depth, and then multiplies it by the width of the soil section. For HSG-A soils with a curve number of 50, their storage potential is 10 inches, as we'll see shortly. So the calculation is the difference between that 10 inches of storage and the 2.4 inches of rainfall, divided by the 2.4 inches of rainfall, then multiplied by the 10-foot width of the soil section. To understand how we get these storage potential values, let's look at the curve number method. We can calculate the potential maximum retention, or S prime, using the formula. S equals 1000 divided by the curve number, minus 10. Applying this for C soils with a curve number of 78, the S value is 2.82 inches. For A soils with a curve number of 50, the S value is a much higher 10 inches. Comparing these values, the 3-year 1-hour storm volume in this region is 2.4 inches. Notice that the A soil's storage potential of 10 inches is significantly greater than this rainfall event, highlighting its high capacity for infiltration. In contrast, C soils with an S of 2.82 inches are closer to the event volume, indicating less additional capacity. As an exercise to deepen your understanding, you could calculate the width of overland flow that can infiltrate a 10-foot wide segment of soil for different curve number values, using the same principles we just discussed. Let's begin our example problem, which focuses on disconnecting DCIA. We'll start by entering the general site information. For the purposes of this walkthrough, the site information has already been pre-filled and is displayed on the screen. Notice that among the various options, the Enter Catchment button is currently the only one active or lit. This is a crucial point. No annual removal analysis can be performed until the necessary catchment data has been entered into the system. You'll also see several yellow information buttons, which are there to provide additional details for the various drop-down menu items and to offer general help as you navigate the interface. We are now entering the watershed characteristics for our proposed design. We have a total impervious area of 1.3 acres. A significant portion of this, 1.1 acres, is being disconnected, meaning its runoff will be directed to pervious areas on site rather than flowing directly into the storm drainage system. This leaves 0.2 acres as directly connected impervious area, which accounts for 10% of our total catchment. Our site features hydrologic soil group A soil, with an associated curve number of 50. In addition to the impervious areas, we have 0.7 acres of pervious area. The act of disconnecting impervious surfaces significantly alters the hydrologic response of the watershed. While the water is routed to pervious areas, we anticipate a potential for a higher overall runoff volume when considering the entire watershed's response. To accurately reflect these changes and calculate the new runoff volume, we will be using a composite curve number calculator. This tool will help us determine the effective curve number for the entire non-directly connected portion of our site. The reason we often use a curve number, or CN, of 95 for impervious areas stems from how runoff coefficients were calculated in the applicant's handbook. Those calculations assumed an initial abstraction of 0.10 inches before any rainfall excess begins. A CN of 95 is precisely associated with this condition, meaning rainfall excess effectively starts once 0.10 inches of rain has fallen. To demonstrate this calculation, we can use the S' equation, which calculates the potential maximum retention after runoff begins. With a CN of 95, S' equals 1,000 divided by 95 minus 10, which results in 0.526 inches. Then, if we calculate the rainfall excess R, using a rainfall amount P of 0.1 inches, and considering the initial abstraction of 0.2 times S', we find that the rainfall excess R is approximately 0. This confirms that at 0.1 inches of rainfall, excess flow just begins with a CN of 95. It's also important to note that the composite curve number is highly sensitive to the fraction of directly connected impervious area, or DCIA, and the size of the pervious areas. Consider this example. If we have a total impervious area where 1.1 acres out of 1.3 acres of the original DCIA are now disconnected, the new effective DCIA is only 0.2 acres. This means a significant portion of the impervious area is no longer directly contributing to runoff downstream. When this disconnected impervious area discharges to a pervious area, the runoff water effectively decreases the storage capacity of that pervious area for subsequent rainfall, which in turn leads to an increase in the effective curve number for that portion of the site. Notice also that this example is based on an HSG-A soil. To calculate the runoff volume, we utilize the composite curve number. This number factors in not only the pervious area, but also the runoff contributed by any disconnected impervious areas. This composite curve number is then brought back to our watershed characteristics worksheet. This allows us to accurately calculate both the post-condition runoff rate of flow and the total runoff volume. Now let's consider a scenario with different soil characteristics. For hydrologic soil group C soils, which have less infiltration capacity, the curve number will be higher. In this example, we're using a curve number of 78. From our proposed design, we still have an impervious area of 1.3 acres, with 1.1 acres disconnected, leaving 0.2 acres as 10% directly connected impervious area. When we re-enter these curve numbers into the worksheet for HSGC soils, the composite curve number for the non-disconnected impervious area becomes 91.26. This significant increase from our initial curve number of 78 demonstrates that disconnecting the directly connected impervious area will result in higher runoff from the remaining non-disconnected impervious area. You might find it beneficial to examine these composite curve number generation calculations yourself to see the impact of other curve values. We're looking at various factors that influence our composite curve number, and it's important to understand why certain calculations are made. For instance, if you were to just take a simple average of the curve numbers, you might get a value like 86.5. However, this method is incorrect and would lead to an underestimation of runoff, which isn't accurate. It's crucial not to use simple averaging or even weighted area averages to calculate runoff, because these methods don't account for the actual weighted runoff volumes, which are used by more accurate calculators. The composite curve number is quite sensitive to both the fraction of directly connected impervious area, or DCIA, and the curve number value assigned to pervious areas. For this example, we're using a curve number of 55 for pervious areas, specifically sandy soil that has been compacted. Normally, natural sandy soil would have a lower curve number, but we've assumed a 10% increase due to compaction, which brought it up from 50 to 55. This adjustment for compaction during construction is sometimes applied in research, based on studies like those by Pitt in 2001, which looked at infiltration through compacted urban soils. The example shows that the composite curve number calculated for this scenario is 83.81, where 1.1 acres of the 1.3 acres of directly connected impervious area were disconnected. It's also important to note that we've gone back to using hydrologic soil group A soils for this calculation, as HSGA is the most common soil type encountered when implementing disconnection practices. Here we're looking at a proposed rain garden design covering about 0.15 acres, with an average depth of 2 feet. Its primary purpose is to protect the groundwater, which it achieves through the use of specific media. The soil type for this particular example is an HSGA soil. For this design, we've selected 7,700 cubic feet of bold and gold media, placed at a depth of 24 inches, providing an additional water storage capacity of 14,200 cubic feet above the media layer. The various input data fields for this design are presented for review. When utilizing any software for hydrological analysis, it's absolutely essential to properly configure your catchments. This critical step involves defining the precise flow of runoff water from one catchment to another. Integral to this configuration is also selecting the appropriate best management practices, or BMPs. It's important to note that the option for multiple BMP selection specifically applies to situations where you're implementing several BMPs in series within the same catchment. Here we're comparing the impact of disconnecting impervious areas versus keeping them connected, and further what happens when a disconnected area also incorporates best management practices. Our example uses 1.1 acres of disconnected impervious area out of a total of 1.3 acres. On A soils, when the DCIA remains fully connected without any BMPs, we observe an annual runoff of about 4.7 acre-feet, which translates to just over 28 inches per year. The total nitrogen load is approximately 10.3 kilograms per year, and the total phosphorus load is around 1.9 kilograms per year. Simply disconnecting this DCIA significantly reduces these values. The annual runoff drops to 2.8 acre-feet, or about 17 inches. Pollutant loads also decrease, with total nitrogen falling to 6.2 kilograms and total phosphorus to 1.1 kilograms per year. This demonstrates a substantial improvement simply through disconnection. However, when we further incorporate a retention BMP alongside the disconnection, the reductions become even more dramatic. Annual runoff falls to a mere 0.32 acre-feet, or just under 2 inches. The total nitrogen load is now only 0.7 kilograms per year, and total phosphorus load is 0.13 kilograms per year. This data clearly illustrates that disconnecting DCIA is highly effective at lowering both runoff volume and pollutant loading. It's important to note that in situations like a basin management action program, if the reductions achieved by simply disconnecting the DCIA meet a target discharge load, then no further BMPs might be immediately required. For context, the precondition runoff, prior to any development, or the post-condition scenario shown, was considerably lower at only 0.19 acre-feet per year, or 1.14 inches per year. This underscores the effectiveness of combining disconnection with BMPs in mitigating the impacts of impervious surfaces. Here, we're looking at a scenario where we're considering disconnecting 1.1 acres of a 1.3 acre directly connected impervious area, or DCIA, and using an A-type soil, typically indicating a soil with good infiltration rates, perhaps in a rain garden application. The key takeaway is that both disconnecting the DCIA and a scenario without disconnecting it can meet the specified performance criteria for pollutant removal and net improvement. However, disconnecting the DCIA offers a significant advantage. It substantially reduces the overall discharge volume. For instance, with the disconnect using an A-type soil, the discharge of total nitrogen is estimated at 1.53 pounds per year, and total phosphorus at 0.283 pounds per year. These values confirm that the performance criteria are met. The speaker notes emphasize that while both methods can achieve the required mass removal of pollutants when best management practices, or BMPs, are in place, the pre-BMP runoff volume without the disconnect would be significantly higher, for example 28.24 inches compared to a much lower volume in the disconnected scenario. Therefore, even though both options achieve the same pollutant removal goals with BMPs, the disconnected approach helps manage runoff volume more effectively. It's also important to remember that in some areas, like those under specific basin management action plans or BMAPs, the focus might be more directly on mass removal rather than just volume reduction. We've covered several key concepts that are crucial for understanding stormwater management. First, it's really important to grasp the value of disconnecting the directly connected impervious area, or DCIA. When we disconnect the DCIA, especially by routing overland flow from impervious surfaces to pervious areas, we can significantly reduce pollutant loadings and runoff. In some cases, simply disconnecting the DCIA effectively can meet discharge loads without needing additional best management practices. A practical example of this is how, for a soils, about 10 feet of overland flow over a pervious area is often sufficient to disconnect the DCIA. To give you a sense of scale, with a composite curve number of 50 and a 10-foot wide pervious area, the runoff from a 32-foot wide impervious area can be effectively stored. This understanding underpins the calculation methods we use for disconnection, particularly when working with the composite curve number calculator. Another important detail we clarified is why a curve number of 95 is used for impervious surfaces when calculating a composite curve number. This specific value ensures consistency with runoff simulations, which typically assume that runoff begins after the first 0.1 inches of rainfall. Finally, we also explored an example project, which serves as a valuable template for you to apply these analytical concepts to similar projects in the future. Remember, beyond just meeting performance standards, factors like surface discharge mass and volume can also be critically important considerations in your designs. This concludes our discussion on how to evaluate a disconnected directly connected impervious area. We encourage you to explore other learning modules if you wish to deepen your understanding or apply to take the self-test. Details for the self-test can be found in its dedicated learning module. Thank you for viewing and listening to this information. This is the last slide of the presentation.